Okay, so think about this for a second. You could toss a pin across your desk, or just picture the Earth spinning right now. That's motion, right? And it's this like ancient puzzle humans have always tried to figure out. How does stuff move? Why does it move?
Exactly.
Yeah.
And that's really what we're diving into today, the absolute bedrock of physics, you
Yeah.
know? It's about the language we use for motion, for force, for how energy gets passed around.
Right.
We'll start with just describing it. That's kinematics. And then we get into the big stuff, Newton, and the reasons things move.
So, our mission for you is to get clear on the essential words, the vocabulary, but maybe more than that, to really feel that huge mental leap, from old ideas to actually being able to predict things with classical mechanics. We
Yeah.
want to boil it down to the concepts that really give you those aha moments. Okay, let's unpack this, starting with just describing motion.
Let's do it. So kinematics
Yeah.
comes from the Greek kinesis, which just means movement. And it's purely about the description. We use quantities like position, how fast position changes, and then how fast that changes.
Which is acceleration.
Which is acceleration, yeah. We're strictly asking how it moves, not worrying about the why just yet.
And right away, we hit this fork in the road. Vectors versus scalars. This feels like the first really crucial distinction.
It absolutely is, because it's all about whether direction matters for what you're measuring. A scalar is, well, simple. It's just got a magnitude, a size, think distance or speed or time, temperature. Just tells you how much.
Like 30 degrees Celsius or 5 kilometers, no direction needed.
Precisely. But vectors. Vectors are where direction is non-negotiable. Things like displacement, velocity, acceleration. They need both how much and which way.
Okay, let's make that concrete. Give us an example.
Sure. Imagine you walk from, say, your apartment to a coffee shop. You might wander around a few blocks, maybe walk 500 meters in total. That 500 meters, that's the distance you traveled. It's a scalar.
It's just the total length of the path.
Right. But your displacement, that's the vector. You draw a straight arrow from your apartment door directly to the coffee shop door. Maybe that straight line is only, I don't know, 200 meters, and it points east.
So the displacement is 200 meters east, magnitude and direction.
You got it. And there's a neat little detail with vectors. That minus sign.
Yeah, what does that mean? It's not just less than zero.
Not in the usual sense. For a vector, a minus sign indicates direction. Usually the opposite of whatever direction we've defined as positive.
Okay, so if velocity is minus 5 meters per second, it just means 5 meters per second going backward or west or whatever the opposite direction is.
Exactly. But, and this is a key point, don't assume anything negative is a vector. Your bank account could be negative, right? Or electrical charge. Still scalars. Direction isn't part of those ideas.
Good reminder. Okay, so building on that, velocity. That's the vector version of speed.
Correct. Velocity is the rate of change of displacement over time. Speed is rate of change of distance. Subtle but critical difference.
And acceleration, rate of change of velocity, also a vector, measured in meters per second squared.
Meters per second squared, yes.
Yeah.
And it's easy to just think speeding up.
But it's more than that.
Oh, yeah. If something accelerates at, say, 2 meters per second squared, its velocity vector changes by 2 meters per second every single second in the direction of that acceleration. Crucially, even if you keep the same speed but change direction, like turning a corner in a car, you are accelerating.
Because the velocity vector changed direction.
Precisely. Velocity changed, so there must have been acceleration.
Okay, graphs. Graphs usually make these things click.
They really do. So plot distance against time. What's the slope? The gradient tell you.
How fast you're going, speed.
Speed, exactly. If we graph that walk to the coffee shop, a steep line means fast walking. A flat line means you stopped, maybe to text someone.
And that slope over a whole section gives the average speed.
But for the speed right now, for instantaneous speed, you need the gradient of the tangent line. Just touch the curve, that single point in time, find the slope of that line.
Okay, makes sense. Now switch graphs. Velocity versus time, the meaning changes, right?
Completely.
Right.
Now, the gradient tells you the acceleration. Steeper slope means greater acceleration.
And the area under the line?
The area under the velocity time graph gives you the displacement.
So if you have positive velocity, the area adds to your forward displacement. Negative velocity
means you're moving backward, and that area under the graph is negative. So it subtracts from your total displacement from the...
Right. Like running forward 50 meters, then back 20. The net displacement is 30 meters forward.
Perfect. And understanding these graphs helps us appreciate the kinematic equations. You often hear them called the Suvat equations.
The predictive tools. Let's just list the variables quickly. C-bowlers for displacement.
Well, for initial velocity, 5-1 velocity, acceleration to your time.
Got it. SUVAT, SUVAT.
And these equations are incredibly useful, but,
Yeah.
this is the big but,
Ah, there's always a catch.
there is, they only work if the acceleration, Lilo, is constant, uniform, not changing.
That is the absolute #1 rule to remember for SUVAT. Cannot stress that enough.
Think of a skier. Nice, smooth slope, constant gradient, friction's constant maybe. Then yeah, acceleration's pretty constant. SUVAT works beautifully to predict their speed at the bottom.
But if the slope changes, or they hit some bumpy bits,
Then acceleration changes, and boom, SUVAT is out the window. The model breaks down. You need a different approach thinking about forces.
it's fascinating, though, that apparently one of those equations, the mean speed one, was figured out way back in the 14th century by scholars at Oxford, long before Galileo.
It really is. Shows
Yeah.
people were chipping away at describing motion for centuries. And that leads us nicely into the causes of motion changes. Because to get to constant acceleration and forces, we first had to ditch Aristotle.
Right, the old idea. For like 2,000 years, everyone figured things just naturally stop.
Yeah, Aristotle's view was that the natural state is rest. To keep something moving, you had to keep pushing it. Stop pushing, it stops. Seems intuitive, right? If you slide a book, it stops.
But it ignores friction, air resistance.
Exactly. And actually, thinkers in the Islamic Golden Age, people like Ibn Sina and al-Baghdadi, they were already proposing ideas much closer to inertia centuries earlier, the idea that motion could continue on its own.
Then Galileo really tackled it head-on with his thought experiments. The inclined planes one is classic.
It is. Ball rolls down one ramp, up another. If there's no friction, it gets back to the same starting height.
But what if the second ramp is horizontal?
Then, theoretically, to try and reach that original height, the ball has to just keep rolling forever on a perfectly smooth, infinite horizontal plane.
Which establishes the idea of inertia. Things resist changes to their motion.
Bingo. And that's Newton's first law in a nutshell. An object stays still or keeps moving at a steady speed in a straight line unless some external net force acts on it.
So force isn't needed to maintain constant velocity motion. Force is needed to change it, to accelerate it.
And that's the gateway to the big one, Newton's second law,
F equals ma.
the equation that changed everything. Force equals mass, big acceleration, Fermi-Galler. It connects the cause, force, with the effect, acceleration. And notice, force and acceleration are vectors. They point in the same direction. A push to the right causes acceleration to the right.
This lets us define the unit of force, the Newton, symbol N.
Yep. 1 Newton is defined as the amount of force needed to make a 1 kilogram mass accelerate at 1 meter per second squared.
Which you said is actually pretty small, like an apple's weight.
Roughly, yeah. A medium apple exerts about 1 Newton of force downwards due to gravity.
Yeah.
It highlights how physics often builds from precise, small-scale definitions to tackle huge problems.
There's another subtle point here about mass itself, isn't there? Inertial versus gravitational mass.
Ah, yes, a really profound point. Inertial mass is the m in Fomalhaut. It measures how much an object resists being accelerated by a force. It's stubbornness.
And gravitational mass.
That's the m in the weight equation, 2F anja. It measures how strongly gravity pulls on an object, or how strongly it interacts with a gravitational field.
And Galileo noticed they seem to be the same.
He did, because when you drop things in a vacuum, a heavy ball and a light ball fall and accelerate at the exact same rate, 2 hours. The only way that works is if their resistance to acceleration, inertial mass, is perfectly proportional to the gravitational force on them, related to gravitational mass.
So they are equivalent.
As far as we can tell, yes. It's called the equivalence principle, and it's a cornerstone of Einstein's general relativity, actually. Incredibly well tested.
Okay, so force causes acceleration. Now we need to talk about interactions, Newton's third law.
The action-reaction law. For every action, there's an equal and opposite reaction.
Sounds simple, but you said this is the most misunderstood one.
Easily. People mess this up constantly. 2 key things to remember. 1, the forces in the pair must be the same type, gravity pairs with gravity, electric pairs with electric. And 2, crucially, the forces act on different objects.
Okay, let's use that classic example. A ball resting on a table. What are the forces?
Right. Force 1, the Earth pulls the ball down. That's the ball's weight, the gravitational force on the ball.
Okay, so the third law reaction pair to that must be?
The gravitational force the ball exerts, pulling the Earth up. Equal force, opposite direction, same type gravity, acting on 2 different objects, ball and Earth.
Wow, okay, so the upward push from the table on the ball the normal force, that's not the reaction to the ball's weight.
Absolutely not. The normal force is an electromagnetic force, atoms in the table, repelling atoms in the ball at the contact surface.
So its third law pair is?
The downward force the ball exerts on the table. Again, equal, opposite, same type, electromagnetic contact, acting on different objects, ball and table.
Got it. That distinction, different objects, is everything.
It really is. And when an object isn't accelerating, like the ball just sitting there, we say it's in translational equilibrium.
Meaning all the forces acting on that one object cancel out. The net force is zero.
Exactly. The downward weight on the ball is perfectly balanced by the upward normal force on the ball. Net force zero, so no acceleration, consistent with Newton's first law. It stays put.
Okay, let's quickly touch on a few specific types of contact forces governed by these laws, maybe three main ones.
Sounds good. First, elastic force. Think springs, rubber bands. Hooke's law describes it. The force needed to stretch or compress a spring is proportional to how much you stretch or compress it. Fumo quish nexikiri. That minus sign is key.
Why the minus?
It means the force the spring exerts back is always opposite to the displacement. Stretch it out, it pulls back. Compress it, it pushes out. It always tries to restore itself to equilibrium. That's what drives oscillations.
Makes sense. Second, buoyancy, floating.
Right. Archimedes' principle. An object immersed in a fluid experiences an upward buoyant force equal to the weight of the fluid it pushes aside, the fluid it displaces.
So why does something float?
Well, fundamentally, fluid pressure increases with depth. So the water pushes up harder on the bottom of the submerged object than it pushes down on the top. If the object is less dense than the fluid overall, it will displace a volume of fluid whose weight equals its own weight before it's fully submerged. Then the buoyant force equals its weight, forces balance, and it floats. Okay.
And the third one, friction between solids.
Yep. Solid friction. We usually split it into two kinds.
Static and dynamic.
Exactly. Static friction is the force that stops something from starting to slide. It can vary, up to a maximum value, FMO1. It matches the pushing force until it hits its limit. Dynamic friction, or kinetic friction, is a force that resists sliding once it's already moving. It's usually a bit less than the maximum static friction, and it's roughly constant, mud, FNR1.
That's why it's harder to get a heavy box moving than to keep it sliding.
Precisely. You have to overcome that higher static friction first.
All right, final big concept, momentum. You mentioned this is conserved, unlike force.
Yes, momentum conservation is huge. Momentum itself, symbol 8 is just mass times velocity, TPMV. And because velocity is a vector, momentum is also a vector, same direction as velocity. Units are kilogram meters per second.
It feels like it captures the oomph of a moving object.
That's a good way to put it. It combines mass and velocity. A slow truck and a fast bullet could have similar momentum. It's about how hard something is to stop.
Like catching a baseball versus a ping pong ball at the same speed? Ouch!
Exactly. The baseball has way more mass, therefore way more momentum, takes a much bigger impulse to stop it.
Impulse. How does that connect?
Impulse links force and momentum change. Remember Newton's second law? Format. Well, acceleration is change in velocity over time, so 5v delta t. So $5 m delta v delta t.
Right.
But the m delta v is the change in momentum, delta p. So $5 at delta p. Delta t, rearrange that. $5 t equals delta p.
Force multiplied up by the time it acts equals the change in momentum.
That's it. That quantity battle delta t is called impulse, symbol $0. Impulse equals the change in momentum. Units are Newton seconds, NSS, which are actually equivalent to kilogram ms.
And this is why airbags work.
Precisely. In a crash, your change in momentum, delta t, is fixed. You're going from some speed to zero. Airbags and seatbelts don't change delta t to t. What they do is increase the time interval over which that change happens.
So if delta t goes up and delta t is constant, the average force, $5, must go down.
Drastically down, making the force survivable. Same idea works for rockets. Huge thrust force comes from ejecting fuel very fast, causing a massive rate of change of momentum. Delta t to t of that.
Amazing. And this leads to the conservation principle.
The conservation of linear momentum. It states that if you have a closed system, meaning no external forces are acting on it, like friction or air resistance, or they all cancel out, then the total momentum of that system cannot change.
Doesn't matter what happens inside. Collisions, explosions.
Nope. The total momentum vector before the interaction must equal the total momentum vector after. It's incredibly fundamental. Holds true everywhere, from billiard balls to particle physics.
They've even found new particles using it.
They have. When experiments showed momentum wasn't conserved in certain nuclear decays, physicists didn't ditch the law. They proposed that an unseen particle must be carrying away the missing momentum. That's how the neutrino was predicted.
Incredible. Okay, that is a huge amount of ground covered. We've gone from basic descriptions, scalars, vectors, through the why with Newton's laws, force, mass, acceleration, interactions, and landed on this crucial conserved quantity, momentum. So, pulling it all together, what's the big takeaway here?
The big takeaway is you now have the conceptual toolkit for classical mechanics. Understanding linear motion, forces, and momentum is the direct stepping stone to understanding rotation torques, angular momentum, how spinning things work. And it's absolutely essential for grasping how fields like electric fields or gravitational fields work by exerting forces on things within them.
Right, it all builds. So, a final thought maybe. We saw the kinematic Suvit equations break down when acceleration wasn't constant, forcing us towards Newton's laws. But even Newton's laws have limits, right? They assume things maybe they shouldn't sometimes.
That's a really important point for how science actually works. Newton's laws themselves are approximations. They break down at very high speeds, near the speed of light, where relativity comes in, or at very small scales, where quantum mechanics takes over. So here's something to ponder. When scientists build a model of reality, how do they know when they're simplifying assumptions, like treating a planet as a point mass, or ignoring air friction on a ball, or assuming mass is constant are no longer good enough?
Hmm.
When do you have to switch to a more complex, maybe messier, but more accurate model? That judgment call, knowing the limits of your model, is a huge part of doing physics.